Hi everyone, I'm Zara from Global AI Hub. Welcome to another series of our webinars. Today we have a really special guest who is Patrick Bangert, who is from Samsung, and he will be speaking about data science workflow. So let's welcome Patrick.
Hi everyone, my name is Patrick.
Hi.
I'm the Vice President for Artificial Intelligence at Samsung SDS. I'm a mathematician by training. I now live in California, working for Samsung SDS and running the AI department where we both develop software and do AI projects in a consulting fashion. And I'll be talking to you today about the workflow of artificial intelligence.
All right then, Patrick, let's get you started. I wish you best of luck, and I'll see you soon.
Thank you very much for having me. Very much appreciated to be part of Global AI Hub and AI Business School.
Likewise.
So I would like to talk to you about the workflow of AI. So this is the outline as far as I see it. The workflow really begins with communication. This is a very important part where basically the data scientist discusses with the group that has the issue, what exactly is it that is the problem? What does the solution look like? What data might you have? What data would you have to acquire on top of what you have? And so on. This is where you define what you want from the solution, what a good solution looks like as opposed to an insufficient solution. And it's really a human-to-human communication where there's a lot of translation involved. Both parties might speak English, but half the party will speak a domain vocabulary and half the party will speak a mathematical data science vocabulary. So it needs a translator to communicate between these two groups. That's actually part of my job, is to be a translator and speak technical English to data science English and backwards. But apart from that communicative aspect, next comes the data acquisition. Hopefully, a lot of the data has already been acquired, but you might want to look, have the right kinds of data been acquired? Has enough data been acquired? And then you need to make that data set clean. That means that any bad data, outliers, measurement errors, and so on have to be removed. And then you have to deal with the gaps, either because the outliers have been taken out, there's a gap that you introduce, or there's a natural gap because your sensor failed or you forgot to record something or whatnot. So you have to decide how are you going to interpolate for those gaps and quantify the uncertainties. So every measurement that you make in the real world has a certain uncertainty attached to it, which means that anything you compute on that basis is uncertain too. So all that has to be quantified. Next, you have to label your data. This is the point where you take your domain knowledge and inject it into the data set by saying, this piece of data is an example of a normal condition or an abnormal condition. This is an example of a cat or a dog or whatever it is that you want to distinguish. The labels have to be put in at this point. And these are the data that you don't measure in the world. These are the data that you introduce as a human being into that data set. Next, you have to select the right features. Some of the features might be present from measurements themselves. If you're going to record time series, for example, if you measure temperatures and pressures, that's a feature in its own right. But you might want to generate what are called synthetic features, which are features that you don't measure in the world. They are features that you computationally generate based on domain knowledge. I know, for example, that if I divide the temperature by the pressure, I receive something useful, something informative about the situation. And that ratio is not something I measure directly. That ratio is something I compute because I know how. But that is, again, a communication between the domain expert and the data scientist that might take some time. Next, I have a completely clean data set that's been added to by these synthetic features. I now have to decide which type of model am I going to choose. Am I going to choose a neural network or a random forest? That's model selection. the algorithm to tune that model to the data that I have is then something that has its own parameters. And those parameters have to be set. Typically, those are set by people, by the data scientists themselves, but it's a manual process. It's trial and error. It takes some time before you hit the right setting. Suppose you do find the right setting. Next, you have to do the full AI training, which usually includes things like cross-validation, where you train the data on multiple sub-selections of your data and test it on the others. And then you can finally deploy your model at inference. Now comes the change management process, because now you want the users of that AI model that you've produced to actually do something with the AI. Up to this point, it's been science. Now it becomes practice, because real people who have nothing to do with all of the science that you did are now supposed to change their life, change their behavior in some fashion based on that AI model. And it's there where perhaps certain issues appear. Now, we have an overview of what the workflow is. Now let me talk about certain aspects of that workflow. It's the communication at the very beginning that represents, in my opinion, 80% of the frustration that you have over the entire project. Because it's there where you have to define clearly what is the problem and what does the solution look like. And if that is not clear, and I mean clear in a mathematical sense, right? Very, very, very precise, then the rest of the project will typically go awry, or you will have to come back to the beginning and start again as people might change their mind. So this is, of course, where the agile process or a Scrum type approach to these things becomes very useful, because let's say you've communicated something in the beginning, you get as far as data labeling, and you discover, actually, guys, the project or the problem is slightly different. The solution has to look slightly different. You go back to the beginning. So that's why I say this is where the frustration happens. However, in contrast, 80% of the risk of your entire project happens at the very end, because there is a good chance that you do everything right, and at the very end, the users say, you know what, actually, what we did the last 50 years is fine. We're not going to change. You know, you did a good job, you scientist people, but never mind. We got this the old-fashioned way. And this happens time and time again. Actually, we find that between 80 and 90% of all data science projects do not get implemented in real life. Some of them don't get implemented because the project itself is somehow substandard, but the vast majority of projects are actually scientifically fine. They don't get adopted because of user issues. Users don't like it. Users don't want to change their life. So the risk is at the very end. So actually, my sort of number one piece of advice to all the data scientists out there is take your users on the journey over the entire workflow so that you mitigate the risk at the very end. Having said that, 80% of the work is in getting a clean data set, right? Once you have a clean data set, the rest is relatively easy. Now, mind you, the rest is the AI part, right? The beginning is cleaning your data, which is largely a task for domain experts, which means that the rest of the AI workflow is not so much work as it is delay, because here you're training AI models, and that might be the simple process of clicking a button, but then having to wait several weeks for the actual training process to complete. So this is the distribution in a kind of Pareto 80-20 rule, in my opinion. Where is the work? Where is the time delay? Where's the risk? So what can we do? So I can't really help with the psychological parts of this. So the frustration and the risk, those are things that are managerial issues that you have to deal with in your projects by human-to-human interaction and planning correctly. It is the 80% of the work and the 80% of the time delay that I really want to talk about in this presentation from an artificial intelligence point of view. And it begins with getting a clean data set. There is a process known as active learning, which can significantly help you by reducing that 80% workload. And it might go something like this. You have to label data. We discussed that in the workflow already. Labeling the data, it looks often something like this. The data would be a picture. On the left-hand side, you have pictures of sheep, and on the right-hand side, you have an X-ray of a person's lungs. And now you want to label certain parts of it. So for example, you want to localize where in the image is a sheep or lungs. You want to maybe identify the individual sheep or the individual lung. You want to see, okay, where's the area that there is a certain thing like sheep, and on the right-hand side, where is the area where the lung is diseased and where is the lung is healthy. Things like that, you would need to have a person do that. So with sheep, of course, any old person like myself can go in and say, okay, here is a sheep. I can draw a rectangle around the sheep. With lungs, for example, when I want to detect, let's say, COVID-19 on the basis of an X-ray of a person's lung, somebody like me can't label that image. I need a professional doctor who has the training to be able to do that. Those doctors are rare, they're busy, they're expensive. Labeling those data sets becomes increasingly harder and increasingly more of a financial investment. So come to the conclusion is that labeling data is an expensive and time-consuming process that involves a lot of work. But the good news is that your entire data set, image by image, doesn't contain the same amount of information. So information is something that is not per image, but some images have more information than others. So very simply put, the trivial example is take an image and copy it. I now have two images, but they're the same. So the amount of information they provide is the same. The information provided by the first image is a certain amount. The information provided by the second image, that's a copy of the first, is nothing at all, because the information is already in the first image. So that should get you to realize that merely increasing the size of my data set doesn't help me at all. I need to increase the information content in my data set. Now, a randomly generated data set, just take as many sheep pictures as you can get or as many COVID X-rays as you can get. That means that labeling the pictures in a random order is going to lead to a lot more work because you're labeling images that add very little information. So there's a law of diminishing returns that you're used to from economics that applies to the case of labeling data. At some point, labeling more images just isn't worth it. The question is, where is that point? And can I somehow move that point up in time to save myself some effort? And the answer, of course, is yes, there is. And it's called active learning. How this works is that you take your entire data set, and at the beginning, you pick a random 1% of it. Okay, so randomly, I pick 1% of the data, I label it. Fine. Now, on the basis of that 1% labeled data, I train a simple, quick-to-train AI model, and I label the other 99% of all the images, and I see where am I very uncertain, where is the model very shaky in its expectation. I take the top 1% of the confused outcomes, and I label them next, and I train the model a second time. I apply that now to the 98% remaining data. And I do the same thing. And you see in the lower image shown on the screen, the red line there shows that as I label 1% and then another percent and another percent, the accuracy goes up quite quickly. And where that dashed green line is at 16%, so 16 of these iterations of getting 1 more percent labeled, retrained, 1 more percent labeled, retrained, after 16 times of this, I get to the maximum accuracy possible. And labeling images beyond that point, the other 84% of the entire data set, labeling them doesn't add any information. So that is active learning, as opposed to what? As opposed to labeling 1% by 1% in random order, which is the blue line that you see on the image down below, which is a very unstructured zigzag where you sometimes get an improvement and sometimes actually a worsening of the accuracy as you go on, but you don't really see structure. Eventually, once you've labeled the entire data set, of course, you will get the same really good accuracy. So what we're talking about here is not getting a model with the maximum accuracy. We're talking about getting a model with the maximum accuracy as fast as possible in terms of the amount of effort of labeling data. So active learning can reduce the amount of human effort that we stick into labeling a data set from 100% down to 16%. So you save yourself a great deal of effort. The next step, if you recall, was feature generation, which is where we approach it from a domain expert's point of view. Again, state of the art is a human process where we have discussions with the experts, we try to implement it, generate some synthetic features from the data set. The point of feature engineering or feature selection is to take a data set that's more or less randomly distributed, like the top image on the right, where you have all these colored dots. So in that sense, the data science aim would be to separate out the colors of the dots and to say, okay, you are a blue dot, you are a red dot. That's the classification task. And so how do we select the features that allow us to do this? This can be automated. There are many algorithms out there to do automated feature engineering for you. And in that sense, you can circumvent having a lot of this domain expert conversations and writing lots of custom computer code to deal with that outcome, is to do it in an automated fashion where these things are detected for you, and therefore the best features are selected and calculated in an automated fashion. An example is in this image in the middle, where we're saying, okay, we start off with a picture of a complete dog, like down below in that green image, and now we take sections of that image. We take the top, the left-hand corner that happens to be the head, or the bottom right-hand corner that happens to be the hind legs, and we say, okay, these are features of the original image because they were part of it. Okay, so the relationship of being part of is an example of being a feature of. So now suddenly, if I see a dog's head in an image, I can conclude, aha, this is an image of a dog. As opposed to when I see an image of a couple of chair legs, I can say, aha, this is an image of a chair. And in that sense, these features can be generated in an automated fashion and learned appropriately. Again, saving you a lot of time of human conversation and specific custom computer implementation. You remember the next step in my process was model selection and hyperparameter tuning. Again, this is the question, which topology of neural network, which kind of AI model, maybe it's a decision tree, maybe it's a neural network, maybe it's a recurrent neural network, maybe it's a support vector machine, whatnot. Ultimately, we don't really care what model it is. just so long as it gets the problem solved that was initially defined. And so which model is best is a matter of trial and error. And state of the art is that the data scientists do that manually. Okay, I'm going to say, okay, now I'm going to try a neural network. Okay, so it's going to take 5 days to run, and then I come back on the weekend and say, okay, let's try a random forest now. And this is a manual trial and error process that, again, it introduces a lot of time delay, introduces human work, and slows down the entire process. This can be automated by doing both the model selection and the hyperparameter tuning simultaneously. Speaking of hyperparameter tuning, what's that? The training algorithm to make the AI model from the data includes parameters of its own right. Now, I'm a mathematician. I could go into this at great depth of detail, but I won't in this presentation. Needless to say, these hyperparameters have a few names that you're welcome to look up in the literature: learning rate, momentum, the size of the mini batch of data that you show at each epoch of training, the number of training epochs before you stop, the amount of dropout, so the amount of neurons in the network that you don't train during a specific epoch. All of that are parameters that are set in advance of training by typically a human data scientist, but it's kind of a quote-unquote black art to design these parameters correctly. The best setting for each one of these hyperparameters is a unique feature of both the model that you've chosen to use for this data set and the data set itself. In other words, if I've discovered that the right learning rate for this problem is a certain number, it doesn't follow that for the next problem that learning rate should be the same. It could be different. So you need to experiment with this, and that is time consuming because, again, you need to do the experiment, think about it, come up with a new setting, try that, and in a more or less intelligent way, either human intelligent or artificially intelligent, to come to the best setting. And that takes, again, time, which produces what I call the 80% time delay in this set. We can do this trial and error manually, which is usually the grid search pattern that is displayed on the left-hand image here, where we say, okay, so we have these hyperparameters. There are maybe 5 or 6 important hyperparameters. And what we're going to do is we're going to do something called design of experiment, where we basically come up with a grid from a minimum value to a maximum value of each one of these hyperparameters, and we're going to make a grid. Okay, so on the image here, I drew, of course, a 2-dimensional grid because that's the screen I've got available. But in real life, it would be a 4, 5, 6-dimensional grid where I might choose 3 or 4 points in each dimension, and that means that I'm going to have to run quite a few experiments, right? As you can see here, with just 2 parameters and 3 values on each one of them, I have to run 9 experiments. Now, each experiment means a full training loop of the AI model, so this could be quite time-consuming to do. Now, I might discover in the process 2 important things. One of the parameters might not have very much influence at all. So I'm actually wasting 6 out of the 9 computations. That's pretty bad. But we can stomach it because all it is effort. The second thing that we're going to notice is that because these 3 points along the spectrum are pretty sparse, if there's a local minimum, which will lead to a high accuracy, I'm just not going to find it. Now, that's worse, because that means not only am I wasting effort, I'm now wasting accuracy. There is actually a much more accurate setting somewhere. I just haven't found it, even though I've searched. So one thing to keep in the back of your mind, and perhaps this is the most important lesson of this presentation, if you go away remembering one thing, remember this. Searching is not the same thing as finding. And grid search is a perfect example. You can perform a grid search and not find the best answer to the question you've asked. The way to approach it is to use an adaptive search, which first performs a grid search and then refines the knowledge of the space depending on the answers it got. And that's what's shown on the right-hand side here, where we do a search adapting to that structure of the top parameter. And we actually find the bottommost point, the best point that gives us the highest accuracy. And the unimportant parameter, well, it doesn't really matter. This adaptive search has another huge advantage over a design of experiment. It's automated. You don't need to do the design of experiment. You can delegate that to the algorithm running the adaptive search, and it will find the best value of the hyperparameters, possibly with the same amount of effort that you would have expended on the grid search. So work smart and not hard to find both the model, the best model to apply to your data, and the best hyperparameters with which to actually train that model. Finally, all of this, the active learning component, the model selection, the hyperparameter tuning, and the feature engineering, all of those algorithms that I outlined to do those things automatically, they can be done automatically, therefore saving a lot of human effort and a lot of time. But what do they have in common? They have one thing in common, and that is trial and error. They involve training the AI model multiple times. The active learning means I have to train a simple AI model after every % of labeling. The feature engineering means I have to do a lot of investigation into my data set and look how they fit together. The model selection and the hyperparameter tuning involve proper trial and error of training the full model again and again and again for various settings. So what's up with that? Well, if we are able to train a model slowly, then all of these things actually don't help us, because all of these processes introduce so much extra training time that it's just going to take forever. So as an underlying piece to all of these automation workflows, we really need something to speed up training quite a lot. And that is distributed training, where you take your training task and you split it across a network of computers. You don't train your model on a single computer on your desktop, for example, but rather you put it on a cluster of computers, and each one of the computers performs a little bit of the task, which means that over the whole network, your task gets done much more quickly. Now, you could do this on your own, of course. You can get yourself a cluster of many computers, and you could, write all the code to get all of these nodes to communicate with each other, get virtual machines set up, get the IP addresses, make sure they can talk to each other in a synchronized and secure fashion, set up all the registries and containers, use all these technologies like Kubernetes and Docker containers and Helm charts, and set up a Horovod system to orchestrate all the jobs. All of this is IT work that, again, is very time consuming. So if you want to do something like this, you would be spending a lot of your time doing IT and not doing data science, which is exhausting and a huge learning curve for data scientists that are not used to all of this high performance computing. What you really want to do is you want to say, okay, I want to do my data science, and I simply want to say, I need to use 64 or 128 or 512 GPUs simultaneously to perform that task. That's what you want to do. And there are technologies out there known as distributed training that will do that for you, where the idea is that you start with choosing the language that you want to do your data science in, for example, TensorFlow, PyTorch, Keras, and whatever else they are. And you don't want to worry about setting up all this IT environment, but rather you want to run your script in that language and get to your results. Now, running that script, that's basically an abbreviation for everything I've set up to this point, right? That's your data augmentation, the active learning, that's the feature selection, that's the model selection, the hyperparameter tuning. All that happens in that script part, and then you want to get to the results. Okay, you can do that by getting the appropriate distributed training tool set up on your network. Now, you don't even have to own, of course, the computers. There are various cloud services that will rent them for you. So you can get all this offsite very easily, and most importantly, very, very quickly. Now, here's an example of what distributed training can do for you. This example is Distilbert, and in case you don't know, Distilbert is a natural language model. It's trained on sentences of a language, such as English, where you always have a set of two sentences. One sentence is the first, and then the second sentence follows it, and you train your network to detect, does the second sentence, in fact, logically follow from the first sentence? And that's trained based on a very large number of documents written by people, so that the Distilbert model effectively can compute the next sentence given any one sentence. That's the technology that's behind all the chatbots that you find online. If you go to a website and this icon pops up in the bottom right-hand corner, which says, okay, hey, this is John, and do you have any questions for me? You can type in a question into that little box, and it gives you an answer. That's not a person. That's an AI natural language model that's doing that for you. You ask a question, it gives you an answer. It's a model such as the Distilbert model that actually does that for you. Now, training a model like this is a very time-consuming task. It can take months on an individual computer. So splitting it across multiple computers becomes very relevant, and it can reduce the training time from weeks to just a few hours. Now, you can see on the image here that as we increase the number of GPUs, the horizontal axis here, the amount of training examples that we can show per second, so examples in hertz, that's number of examples per second, increases linearly. Now, linearly is a very, very nice property to have. If I double the number of GPUs, I also double the amount of examples I can show to the training algorithm every second. Now, trivially, you would expect that, right? Recall our elementary school homework. If it takes one builder 100 hours to build a house, how many hours do 100 builders need? Well, the supposed answer is 1 hour, right? Now, of course, in real life, it's not 1 hour, because introducing these 100 builders means I need to have overhead. I need to have management and orchestration behind all of these. And so we would expect that as you increase the number of workers on a task, each additional worker offers only an incremental improvement. Well, in this case, we're actually able to orchestrate the IT environment in a way that really scales linearly. Each additional GPU adds a full GPU's worth of resources. Not only that, if you look at it in detail, you can in fact see that as you increase the number of GPUs from 1 computer to 8 computers, so you increase the resources by 8, the speed goes up by more than 8. It goes up by over 13 times. So in fact, not only do you reduce the overall duration by introducing more and more and more GPUs, you actually accelerate beyond the linear scaling. You go into a hyper training mode where you actually gain time itself, time per GPU. So increasing the resources by 8 increases the speed by 13.6 times. And that is the case because each GPU has a certain amount of memory, so you can include more training examples in the active RAM memory of each of the GPUs, providing you that superlinear scaling And so distributed training does not just consume more resources, it actually consumes less resources than training it on individual GPUs. And that, computer memory is the reason for that. So distributed training improves the speed a lot, which then enables you to do all the other things I've been talking about and get finally to a more accurate model in the end with less human involvement and with less total time. So in conclusion, there's nothing much that I can do about the frustration and the project risk. Both of those are management topics. And if you wanted to, we could have a whole presentation like this about some of the management pros and cons of the data science workflow to alleviate or at least mitigate both the frustration and the risk. What I've been talking about mostly here is reducing the workload during the data science task for the people involved, and using the active learning component can reduce the total amount of human work by 1/2. Now that's very significant if you think that the typical data science project might take a couple of person years to complete. Reducing the work by 1/2 would save you the equivalent of perhaps 1 to 1.5 years of salary for a data scientist. So that's a significant reduction in cost and work. Also increases the amount of projects you can do with the given size team. On the other hand, the time delay, which is all the fact that you have to run these AI models multiple times, the time delay can be reduced. Now, I'm not giving a percentage here because it depends on the number of computers you have available. As I said, it scales linearly. The more computers you use, the more time reduction you can get. You can essentially remove the time delay altogether if you only use enough resources. And these resources are in fact available. Again, if you go to one of the cloud providers, they will provide essentially an arbitrary amount of resources to you to be able to run all of these projects. So simply put, the amount of human work can be cut in half, and the amount of time delay for the AI portion of the data science project can be cut into whatever small fraction you desire by simply increasing the number of computers involved. So that, ladies and gentlemen, is the data science workflow in my personal opinion. Now, all of this, of course, can actually be done in real life. And I welcome you all to reach out to me. You can reach out to me on LinkedIn, for example, or through the organizers. And I will put my contact details here. Patrick Bangert, if you want to reach me, here's my email and phone number. And this is done by Samsung SDS, the company I work for. We produce a product called the Brightix AI Accelerator, which does many of the things that I've been illustrating. And we do that, of course, in collaboration with a number of partners of ours, such as Amazon Web Services, where you can get the computers, NVIDIA that makes the GPUs, NetApp that makes the storage servers, Mipsology allows you to export that to edge devices such as the FPGA that's popular in things like autonomous vehicles, to get a finished AI product actually deployable on portable systems. So thank you very much for your attention, and I look forward to getting some questions here or your reach out messages later on. Thank you.
All right, it was a great talk. Thanks a lot for your talk. I had one question to ask you. Basically, if you have like a really, like you're a company, fine, you have like a decent IT system, but imagine you don't want to invest too much in getting like a lot of computers or anything. So how could you solve that problem? Like, would a cloud be able, like a cloud-based service, be able to accommodate, for example, like a project which like in a company which is like, has like 5,000 plus employees, like a very large scale project, for instance?
Yeah, so the answer is simple. If you don't want to purchase your own hardware, then that's what the cloud is for. So there are these three famous hyperscalers Google Cloud, Azure Cloud from Microsoft, and Amazon Web Services that will supply that infrastructure for you at a certain cost. It has to be noted that the cost is roughly an order of magnitude greater than the cost of buying your own hardware. So if your project is relatively short, the cloud is a fantastic idea. If your project is long, or you think that you will have several projects that will keep those computers busy for a number of months, it will be cheaper to actually purchase your own hardware and set all that up.
But isn't that like a really, like long drawn out investment? Like imagine purchasing, sourcing computers, getting them installed, having like a specific space set up for them. So doesn't that kind of like really increase the time delay that you were talking about?
Of course, it requires some time delay to purchase your own cluster and set that up. Of course, that you would only do once. And then the second project would have those resources available for you immediately in your own, in your own backyard. If you do it on a hyperscaler cloud, of course, you don't have that time delay, but you have to pay the price. There is sort of a third alternative, which is to get a system integrator to do that job for you. And of course, Samsung SDS is well placed to do that on your behalf. If you want us to construct a data center for you, we'll be very happy to do that. Then that's the middle path.
That was really smart and really smooth, I should say. That was a good one. I should learn from you.
Thank you.
Anyway, so it was great having you here, and I hope we have you here soon. I really enjoyed your talk. Since we don't have any comments, so I just had my question to ask. So do you have like any closing remarks or anything you want to say to the people watching?
Well, I just want to say thank you very much for being here, for listening to me ramble on for almost an hour. That's very kind of you. I hope it's been of interest to talk about the data science AI section. As I said, there's a lot to be said about the managerial parts that I didn't go into. Those have to be watched out for, definitely. And once again, the invitation goes out to everybody. If you have any further questions and you feel too shy to ask here in a live session, feel free to reach out. Thank you for your attention.
Thank you. I think we're gonna have like other talk with you, or just over like the managerial risks and problems.
Thank you.
Yeah, so it was great listening to you. Thank you so much for your time, and hope you have a nice day ahead.
Thank you. You too.
Thank you.
Bye, everyone.
Thank you, everyone, for tuning in. We will have another webinar 2 weeks from now, so I hope to see everyone there. Have a nice day. Bye-bye.